Okay, we're moving on to the next lesson now, 17.5, Gibbs and work. And we want to find out how Gibbs free energy is related to work and how can we make an unfavorable reaction go forward in general using work.
So Gibbs free energy, delta G equals work max. It means that the free energy means this is the energy that's available or free to do work on another system. The maximum amount of work we're going to get out of the process is what delta G equals. But we're never going to be able to fully utilize all of that work. Some of the energy is always going to be lost to increasing the entropy of the universe. So another aspect of the second law of thermo is that no process is 100% efficient. We can't convert all of the chemical energy in a reaction, for example, into electrical energy in a battery. We can't turn all of the mechanical energy coming from, say, a steam turbine, like steam blowing on a fan and turning the turbine. We can't turn all of the energy into electrical energy in a generator to make electricity. We will always lose some of that energy. Nothing is 100% efficient. There's no perpetual motion machine. So a perpetual motion machine is actually kind of like an engineering joke. It's the idea that I can start something up by applying some work or putting some energy into the system, and then the system is going to create energy in order to keep itself going. And this just isn't possible. It's never going to work. If you had a pendulum, for example, and you pull the pendulum back and let it go, it's going to swing back and forth and back and forth and back and forth, but eventually it's going to stop. No matter how frictionless you make the bearing that holds the top of that pendulum, it's going to stop eventually. Nothing can go forever. There is no perpetual motion where it continues adding energy back into the system. Energy is always lost. So another way of looking at the laws of thermodynamics, the first law, you can't win. You can only break even. There's a constant amount of energy in the universe. You cannot create more energy out of nothing. So the best you can hope to do is just break even. Whatever energy you started with, that's how much you're going to end up with. You're never going to get more. The second law then says, well, actually, you can't even break it even. You're not even going to be able to use all of the energy that's available. So there's a constant amount of energy in the universe, but most of it is too dispersed to be useful. So, for example, when we dig oil or coal up out of the ground and we burn it to get energy, it took millions of years to concentrate that energy into the oil and coal, and then we burn it and we dispersed it. It's still there, but we're not going to be able to get it back and replace it and turn it back into oil. That's why we need other sources of energies, because we're going to run out of fossil fuels. Once we've burned all those fossil fuels away, that's it. We dispersed all the energy. We don't have any real way of turning that energy back into something we can burn again. So when you use energy to do work, it's becoming more dispersed. The entropy is increasing. And once you've dispersed it, it's no longer useful energy that you can harness. So the laws of thermo are telling us that even though there is a constant amount of energy, there is not a constant amount of free or useful energy. Once you do work with it, you've increased the entropy of the universe and you've lost some of it. Unfavorable reaction. If a reaction is unfavorable, then we have to apply work to force it to happen. We've talked about that already. That would mean that in this case, delta G equals work minimum, the minimum amount of work it's going to take for you to force that reaction to go backwards. It's the minimum amount that we have to apply because we always have to actually apply more than that. We will actually have to apply more than the delta G value because the entropy of the universe is going to have to increase. Nothing is 100% efficient. There's no way that we can apply just delta G and achieve what we want to achieve. We're always going to have to push a little bit harder. So how do you make it go? How can we make an unfavorable reaction go forward? How do we actually apply work to it? We're going to talk about two examples. One is to apply electricity, and the other is coupled reactions. So in the first one, let's talk about starting your car. If you turn the key in the car or push the button, if that's the kind of car you have, then the car battery is going to produce electricity via a thermodynamically favored reaction. That's how batteries work. It's a thermodynamically favored reaction producing electricity. We will use some of that electricity to then start the motor of the car. Now the car started and it's burning gasoline, assuming you have a gas-powered car. Now that the engine is burning gasoline, it is producing energy from a different source. It's burning the gasoline now, not from this battery. And some of that energy can then be used to recharge the battery while the car is running. So your gasoline engine is driving the wheels on your car, it's making your car go forward, but some of that energy is siphoned off and sent back to the battery. It's sent back to the battery's electricity to recharge that battery so that the next time you want to start your car, the battery still has power. So you can get the battery back up to its original charge, but the surroundings cannot return to their original state because the entropy change of the universe, it has to be greater than zero. The entropy of the universe always has to increase. So if we decrease the entropy of the battery by recharging it, our surroundings are going to have to get messier, going to have more entropy. So we can keep recharging that battery, but we're still losing some of that energy. It's not a perfect cycle. And of course, you know from your own cell phone, for example, that eventually it stops recharging. You can only recharge it so many times. That's part of an entropy effect too. Things fall apart, things break down, things get messier. You can't get it perfectly back to the same state again because the entropy of the universe is always increasing. Another example, extracting metals from ore. So ore means I'm going to dig up rock out of the ground. Let's say I dig up some rock that contains zinc sulfide. That's a compound, ionic compound, but I don't want zinc sulfide, I just want zinc. I want to make something out of pure zinc metal. So I need to find a way to decompose the zinc sulfide and turn it into zinc and sulfur separately. So that's a decomposition reaction. I would have to apply work, meaning heat it up, to make that happen. It is not thermodynamically favorable. Delta G is a positive value, doesn't want to happen, so I'm going to have to force it to happen. So I could heat it up, but there's another option. We could couple the reaction with a favorable one. Then we don't have to do any work. Both of the reactions will go forward. So let's look at what that means. Here's the same reaction I showed you a second ago. This is us trying to separate the zinc from the sulfur. Second reaction, sulfur reacting with oxygen to make sulfur dioxide. Here delta G is negative. This is thermodynamically favorable. It will go forward. It will happen on its own. Let's add them up. Looks just like Hess's law. The sulfurs cancel out. Here's everything that's left. We can add up the delta G values just like we used to add up delta H values. Nothing different there. So this delta G is negative, thermodynamically favorable. This reaction will go forward. If we react zinc sulfide with oxygen, we're going to be able to get pure zinc. So rather than heating the zinc sulfide, we're just going to react it with oxygen. We have to apply less work to make it happen. We still get the pure zinc. We do get sulfur dioxide instead of pure sulfur, so if that matters, well then this particular set of coupled reactions isn't going to help you. But as long as it's the zinc you're really interested in and you don't mind having sulfur dioxide, then it works, it's fine. So the reaction's favorable, but do you think it's actually going to occur at room temperature? Hopefully you decided no, because I'm asking you the question, but also because, think about it, if this reaction was going to happen all on its own, all the time, then why would we be digging up zinc sulfide in the first place? There's oxygen everywhere. As soon as you expose the ore to air, as soon as you dig up this rock, wouldn't it just immediately turn into zinc? So that should be easy. We're getting zinc, pure zinc metal easily. That isn't what's going to happen. This reaction is thermodynamically favorable, but it is not kinetically favorable. It's very, very slow. It has a high activation energy. And remember, that's two different issues, whether it's thermodynamically favorable or kinetically favorable, two different questions. So this reaction will probably be very, very slow. So what could you do to speed it up? And hopefully you all just said, find a catalyst. Yes, find a catalyst, then you can speed up the reaction so that it actually occurs at a decent rate and we can make our product. So we say that this reaction is under kinetic control, but at least it's no longer under thermodynamic control. If it's under thermodynamic control, then that's like saying it's just not going to happen unless I put in a whole lot of effort. Now that it's thermodynamically favored, I just need to get a catalyst to make it go a little faster. It's going to happen, and it's not going to take me a whole lot of work and effort to make it happen. I just want it to happen at a reasonable pace, so I'll find a catalyst. Last thing, ADP-ATP cycle. This is a biology thing, and I know you learned this already. Bozeman mentions it in video number 60, so I would recommend that you go watch Bozeman video number 60. He gives several examples of coupled reactions, including the ADP-ATP cycle. There's no way I could explain it any better than he does because it's a biology thing, and I honestly don't know any more than what he's about to tell you. And I know you already learned it, but I know it's a favorite example of college boards, so this concept could show up on the AP exam. That's why I want you to go back and watch that video and remind yourself, what does this mean and how does it work? Because it's a very common example of coupled reactions. So please go watch that video. Check it out. All right, we're done. Here is your classwork. This says chapter 17. I checked the numbers, and in the electronic version, it's chapter 18, but it's the same problem numbers. So you're still looking at the same numbers, just look up chapter 18 instead. Don't get wound up about sig fig here. There's some weird sig fig issues in these problems, and I just don't think it's worth stressing out about. I cannot find very much consistency in the key or in the book that I can see where one thing is always right. I've never seen them count sig figs in this type of problem. We're just gonna sort of let it go. Okay, put it on the back burner. It's more important just to be able to basically do the calculation than it is to make sure we know exactly what the right sig figs are. Don't go wild. Don't put 15 digits on there. It's never going to be that much. That's it. Okay, bye.